Here's sample test 4, problem number 4. Two parallel conductors carry current in opposite directions as shown in the figure at left. One conductor carries a current of 6 amps. Point A is at the midpoint between the wires and point C is at a distance d to the right of the 6 amp current. If d is equal to 10 centimeters and I is adjusted so that the magnetic field at C is 0, find the value of the current I. Alright, so we have these two wires, and we have them separated by a distance d, which is 0.1 meters. And point C is also 0.1 meters to the right of the second wire, which is 6 amps. Sounds good. And we have no net magnetic field at point C. Now if we use the right-hand rule from wire number A, we have a current coming down like this, and if you point your thumb in the direction of that current, your fingers will be coming out of the page to the right of that wire. So at point C, we will have a magnetic field that's called B1 that is coming out of the page. For wire number 2, we have a current that's going up here. Let's call this 2. Let's call this 1. For wire number 2, if you point your thumb in that direction, then the magnetic field due to that wire will be going into the page at point C. So these two fields will be in opposite directions at point C. If they have the same magnitude, then the net field at C will be 0, and that's what we want. So we want that the magnetic field due to wire number 1, which is mu naught I1 over 2 pi, let's say R1, we want that to be equal to the magnetic field due to wire number 2, which would be mu naught I2 over 2 pi R2, because they're in opposite directions and they'll cancel out then. Well, the mu naughts cancel out, the 2 pi's cancel out, and we want to find I1, so I1 is going to equal R1 divided by R2 times I2. R1 is actually equal to 2D because we're 2D away from wire number 1. R2 is D and I2 is 6 amps. So with the D's canceling out, we have that I1 is actually equal to 12 amps. Sounds good. What is the value of the magnetic field at point A? Now at point A, B1 is again coming out of the page due to the right-hand rule of wire number 1. But due to wire number 2, if you point your thumb in the direction of that wire, you will also get a magnetic field coming out of the page at point A. So that's B2. So these two fields will both be coming out of the page. So the magnetic field at A is going to be equal to the magnetic field due to wire 1 plus the magnetic field due to wire number 2, both coming out of the page. So this is going to be equal to mu naught I1 over 2 pi R1 plus mu naught I2 over 2 pi R2. So this is going to be mu naught, which is 4 pi times 10 to the minus 7 over 2 pi times I1, which is 12 amps, over R1, which is 1/2 D, which is going to be 0.05 meters, plus I2, which is 6 amps, and it is also half of a D away, 0.05 meters away. So 4 pi divided by 2 pi will leave us a 2 there. And this is equal to, let's go one step further. So this is 2 times 10 to the minus 7. And then we're going to have 18 divided by 5 times 10 to the minus 2. And then this is equal to 36 divided by 5, which would be 7.2 times 10 to the minus 5 Tesla. And it would be out of the page towards you. Sounds good. What is the force per length between these wires? All right. Well, that's a separate equation. We got the force per length is equal to mu naught I1 I2 over 2 pi d, where d is the distance between the wires. So this is going to be 4 pi from mu naught times 10 to the minus 7 times I1, which is 12 amps, I2 6 amps, over 2 pi, and d is 0.1 meters. So 4 pi divided by 2 pi leaves us a 2. So we're going to have 12 times 12, which is 144, times 10 to the minus 7 over 10 to the minus 1, or 0.1, which is going to be 144 times 10 to the minus 6, which would be 1.44 times 10 to the minus 4 newtons per meter. So that is the force per length between these two wires, 1.44 times 10 to the minus 4 newtons per meter. And it should be repulsive because the currents are in opposite directions.